All right, today we're diving into a true legend in the world of AI. It's an algorithm that, kind of quietly, became one of the most important tools for training the deep learning models we use every single day. We are, of course, talking about Adam. It really does feel like magic sometimes, doesn't it? But behind the curtain, it's all about this process called optimization. Basically, the art of finding the best possible settings for a model. And to really get why Adam was such a game changer, we first have to understand the problem it was designed to solve. So here's our game plan. We're going to start with the fundamental challenge that all optimizers face. Then we'll introduce Adam and see how it cleverly mashed up the best ideas that came before it. After that, we'll pop the hood and see how it works, look at the actual data on how it performed, and finally, really dig into its lasting legacy. Okay, so the main job for any machine learning optimizer is to minimize mistakes, to reduce the error. Imagine you're trying to find the absolute lowest point in a huge, sprawling mountain range, but you're blindfolded. The only thing you can do is feel the slope right where you're standing and take a step downhill. That's the challenge. For a long time, the main way to do this was something called stochastic gradient descent, or SGD. It's a really elegant, simple idea. Figure out the slope, that's the gradient, right where you are, and just take a small step in the steepest downward direction. You do that thousands, maybe millions of times, and eventually you should end up in a valley. The stochastic part just means you're not looking at all your data at once, just small random batches to keep things moving. But, this classic method wasn't perfect. Far from it. It could be painfully slow. The steps could be really jumpy and noisy, sometimes leaping right over the target. And here's the real kicker. You had to manually, by hand, pick the size of every single step. That's the learning rate. If you got that number wrong, your model might just wander around forever and never learn anything useful. So the field was desperate for something smarter. And then, in 2015, that smarter something arrived. Enter Adam. This wasn't just some tiny little tweak. No, this was a whole new way of thinking about how to get down that mountain. And the name itself, Adam, actually tells you a lot. It stands for Adaptive Moment Estimation. It's adaptive because it doesn't just use one fixed step size for every part of the model. Instead, it calculates a custom learning rate for every single parameter, and it's constantly adjusting them as it goes. It does this by keeping track of the moments, which is really just a fancy stats term for the mean and the variance of the slopes it's seen in the past. Now, the creators, Diederik Kingma and Jimmy Bay, didn't just pull this out of a hat. As they say right there in their paper, Adam was this brilliant synthesis. It was specifically designed to take the absolute best parts of two other popular optimizers at the time, AdaGrad and RMSProp, and merge them into one powerhouse algorithm. And this combination was the secret sauce. Adam took AdaGrad's superpower, which was handling sparse data, super common in things like text analysis, and fused it with RMSProp's ability to deal with situations where the target is always moving. Adam got the best of both worlds. Okay, so how does it actually do all of this? How does it perform this magic? Well, the whole algorithm is really built on two main ideas, momentum and adaptive scaling. Let's pop the hood and see how the engine really works. So here's the play-by-play for every single step Adam takes. First, just like good old SGD, it figures out the current slope. But then it does something new. It updates a running average of the past slopes. That's the first moment. This is like momentum. Think of a bowling ball rolling downhill. It smooths out the journey and helps it power through little bumps. At the same time, it updates a running average of the squared slopes, the second moment. And this is what helps it shrink or grow the step size. Finally, after a quick but super important bias correction, it takes its smart, calculated step. And I can't overstate how important that bias correction step is. See, right at the start of training, those running averages are basically zero. Without this little correction, the algorithm could take these massive, wild steps right at the beginning and totally mess everything up. It's a small detail, but it's what makes Adam so stable and reliable. Okay, so that's the theory. It sounds great, right? But does it actually work any better in the real world? Well, the original paper put it to the test, pitting Adam against the other leading optimizers in a series of head-to-head competitions. On a pretty straightforward task, classifying handwritten digits, Adam performed like a champ. As you can see from the chart, Adam and a carefully tuned version of SGD got to about the same low error rate, and they both beat AdaGrad. This proved that even on the simple stuff, Adam was a top contender right out of the box. But where Adam really started to pull away was on the more complex, messy problems.
look at this. The difference is even more obvious. You see that atom bar on the far right? It's the lowest by a good margin. It achieved a lower error, meaning it learned better. It just seems to handle the chaos of deep learning more effectively. And it wasn't just about getting a better answer, it was about getting there fast. When they compared it to another more complicated method, Atom was a total speed demon. Every single step was 5 to 10 times faster. I mean, that's a huge difference when your model might need to train for days or even weeks.
And on deep convolutional networks, the kind that power image recognition, the results were just night and day. Just look at that huge bar for Atagrad on the left. It basically just gave up. Its progress completely stalled. Atom and SGD, on the other hand, kept on learning and found a much, much better solution. It just showed how versatile this new algorithm was. So, after seeing all this evidence, it's really no surprise what happened next. Atom quickly became the default choice, the go-to optimizer for researchers and engineers all over the world. So what was this winning formula? Well, it's fast, it doesn't need a lot of memory, and it can handle huge models with tons of data. But the real game changer, the thing that made everyone fall in love with it, was that last point. You barely had to tune it. It just worked right out of the box on an incredible range of problems. And for anyone who spent days fiddling with learning rates, that was a miracle. So at the end of the day, Atom's legacy isn't just about faster training times or slightly lower error rates. Its real impact was that it made this ridiculously difficult process of optimization feel, well, manageable. It made it more robust and straightforward. And in doing so, it helped democratize deep learning, opening the doors for way more people to build and experiment with these amazing models. And that brings us to one last thought. Atom was a brilliant solution for the challenges of 2015. But the models we're building today are thousands, even millions of times larger. The mountain ranges we're trying to navigate are almost unimaginably complex. So it really makes you wonder, what will the next Atom look like? And what incredible new things will it allow us to build?